Yes, question?
So could you fix that by making like first order derivative approximation that have three terms, so like ui, ui minus 1, and like ui plus 1?
Yes, that's what I'm going to be talking about. So yes, how about the suggestion of let's actually use more terms, right? So for example, we know we can do better than first order by approximating the solution as ui plus 1 minus ui minus 1 divided by 2 delta x. So this is the central difference, right? This actually we know if we are only allowed to use I plus 1, I and I minus 1, this is the most accurate scheme we can come up with, right? So going back to our finite difference lecture, we have three numbers to play with, the coefficient before ui minus 1, ui, and ui plus 1. So we have three unknowns, and we can satisfy three equations, which means we can cancel three terms in the Taylor series analysis. We can cancel the constant term, we can have the derivative term to come up to be exactly what we want to approximate, the second equation, and then we can cancel the second order derivative term, right, which gets rid of this first order diffusion, numerical dissipation. So the resulting scheme is actually the central difference. So what's the behavior of the central difference? That can actually be easily evaluated by just modifying this line, right? So this is first order upwind. So let's code up a second order scheme. So the second order scheme is actually ui plus 1, which here is u to 2 to the end, and u1, right? This is ui plus 1. ui minus 1 is the same thing as I coded before, and instead of dividing by delta x, I divide by 2 delta x. So, right, so that's the second order scheme. Now let's do this again and plot the solution of the second order scheme. We see that. Okay, so now it's a little bit more difficult to interpret just by looking at the plots over all time steps. So let's just plot u at the last time step. So this is the solution of the square wave advected over one period. Okay, so why is it all over the place? Let's actually look into the modified equation analysis. Actually, before doing this, let's actually a more easier to analyze position. Maybe just look at a few time steps after the initial condition, right? So this is a few time steps after the initial condition. We see that we still have almost like a square wave. But if you look carefully, if your eyes are good, you can see the square wave now already starting to deform, right? And if you look at, for example, 50 time steps, you can see that there are more deformations. It basically looking like there are some high frequency oscillations appearing near the sharp discontinuities. So why is that the case? Now let's perform modified equation analysis to see if we can gain some information from such analysis. And we'll turn out that the additional term that comes out of the modified equation analysis actually points to what's called the numerical dispersion as opposed to dissipation. And the result of dispersion is actually that. Okay, let's start the analysis. ui plus 1 is actually equal to ui plus delta x times u prime, which is the first order derivative, plus half of delta x square times u double prime, the second order derivative. This is basically standard Taylor series analysis, times the cubic term is multiplied by third order derivative. So let's stop over here and just say it's O delta x to the fourth, which is everything proportional to delta x to the fourth and higher powers. ui minus 1 is practically the same, especially everywhere you see delta x, you replace by minus delta x. The square terms are going to be the same because minus delta x square is actually delta x squared. The cubic terms are going to be negative. Okay. Now with that, let's see what our ui plus 1 minus ui minus 1 divided by 2 delta x is. This term gets cancelled out. This term becomes exactly u prime. This term gets cancelled out again, but this term is still here, right? This term becomes, I think it's plus the two ones gets added together, but it's divided by 2. So we again get 1 over 6 times delta x squared times u third derivative plus O delta x cube, right? Because this delta x to the fourth divided by delta x is delta x cubed. So that means this numerical scheme is actually a pretty high order approximation for this differential equation if you plug this side into the differential equation. It is equal to du dt plus du dx, which is this term, then plus a 6 delta x squared times the third order derivative of u is equal to 0. So this is actually a third order, at least a third order approximation to this equation. I think it actually turns out to be a fourth order approximation, because if you actually expand the delta x to the fourth term, it is also going to cancel out, right, because of the symmetry. Anyway, so actually let me just say it's actually a fourth order approximation to this equation. So what is this equation? This equation is a linear advection equation with a third order dispersion. So this is dispersion.